Welcome to this special Sunday edition of Code Along with Alex. Today we're going to dive into Rust again and look at types. So let's get going. To start, we're going to check the docs, 'cause that's always the best place to start. And today we're going to cover types, like I mentioned a few moments ago. So Rust provides several mechanisms to change or define the type of primitive and user-defined types. In the following sections cover casting between primitive types, specifying the desired type of literals, using type inference, and aliasing types. So we'll jump into the code in a quick second, but let's just read a little bit. So Rust provides no implicit type conversion, also called coercion, between primitive types, but explicit type conversion, also called casting, can be performed using the as keyword. Rules for converting between integral types follow C conventions generally, except in cases where C has undefined behavior. The behavior of all casts between integral types is well defined in Rust. Let's get to coding. So I'm going to create a new directory for today's work, or a new subdirectory in our repo. We'll call it o5_casting, or actually o5_types. And now let's change into that directory. Okay. Now let's use cargo to create a new project for us. We'll call it casting. And then if we expand the folder tree in VS Code, we can see that there's an O5 casting, and then there's a main.rs provided for us. And as usual, we'll delete the boilerplate. Hello world. Okay, so to start, we're going to use one of the warning suppressions for Rust because the compiler is very particular about doing things such as unused code or unused code. So today we're going to suppress warnings from casts which overflow, and we'll dive into that in a moment. But that's likely due to or related to casting between like integer types and some types which don't have the sufficient bit depth to represent the values of other types, and so overflow will occur. But Rust has some ways to manage that, which we'll likely see today. So we're just going to allow for overflowing literals in our code. And we can comment that out in a bit to see what the code or what the compiler will do. So to start, let's just kind of create some decimal value. I'm just going to pick some random numbers. And then we're going to add the F32 kind of suffix to denote that it's a float 32. Next, let's declare an integer, but we're going to be a little tricky and try to mess with the compiler, see if that works. I don't expect it to because we're trying to set an integer of type unsigned integer 8 or a variable of unsigned integer 8 to a decimal of float 32. So I expect this to yell at us. So actually we can save right now and do cargo run to compile and run the program. And then the compiler will let us know if this is chill or not, which I expect it to be not chill. Yes. And I'm in the wrong folder. That always happens. Okay. Change into the correct subdirectory and then do cargo run again. And you can see we got some errors. We expected integer to be unsigned 8, but it found F32. Okay. Let's comment that out. Rerun our code. This should not error. Yeah, I made it just some warnings because that's fine. Unused variables. That's chill. We'll use it in a moment. So next, let's do some explicit conversion. So our first kind of declaration didn't work. Sorry about that. So now let's try to do some conversion. So again, we'll have a variable integer, and then we're again trying to set it to decimal, but we're going to convert it to as U8. And then let character equals integer as character. Will this work? We'll print these out in a moment, but I just want to see if we get any errors. I don't expect it to, because the as utility should help us. Or the as keyword. Excuse me, it's not a utility. Okay, yeah, just unused code. Otherwise, it looks fine. Okay. And then let's try this. One last value. Can we convert decimal? To character? Maybe. I don't know. No. Okay. Char from U32. Invalid cast. So not all casts are valid. Interesting. Only unsigned 8 can be cast as char, not float 32. Good to know. The compiler is super expressive with letting us know what we need to fix in our code, so I encourage you to read through the error messages. It will really help you out. Okay, so now let's just invoke our println macro like we usually do and see what these look like in a more, or in an actual human readable form. Because we've been kind of just verifying through error codes or lack thereof. But let's actually see what this looks like. So we're just creating a string with some empty braces that we're going to use some string interpolation. I don't know if that's the actually correct term in Rust, but that's what I've heard in other languages. This general process. Cool. And I spelled castings wrong. Or casings. Yeah, castings. Excuse me. But you can see the initial value is 859.32, which we declared in decimal. When that is converted to U8, that becomes 255, which is the maximum value of type U8. And then if we convert integer to a character, that becomes Y with an umlaut on top. So that is very interesting. Cool. Just gonna denote it doesn't work. Okay. Next, let's get into a little bit more printing and integrating the conversion into a print statement. All right. To start, invoke our println macro. So we're going to do 1,000 as the U16 is 1,000 as U16. And then let's also do this as U8. I just did some copy paste to save time. But feel free to type it all out if that's what you prefer. Okay. Let's see what happens. So 1,000 as U16 is 1,000. 1,000 as U8 is 232. Weird. So the logic behind that, as described in the docs, is 1,000 minus 256 minus 256 minus 256 equals 232, which is weird. But that's the logic. Okay. We can do the same thing with some negative values, but it's not super exciting. So I'm going to skip that. I guess to finish, we'll, at least with casting, we'll look into some of the float behavior. So let's do a couple more println macros, and then we'll move on. There's only so much of this I can stomach in one sitting before my brain gets a little woozy. So again, we're using the float32 kind of suffix with the underscore, and then we're going to cast it or convert it to a U8. And next, I'm just going to copy paste this so I don't have to type that all out again. Very similar expression, but change this to negative 100 instead of positive 300. And now we're going to try to cast this negative signed integer to an unsigned integer type. And then to finish, we'll do one more. And this one, we're going to explore nan. Didn't know you could do this in Rust, so that's cool. So yeah, that's how you can get nan pretty conveniently. float32 and then nan. All right, let's save this, run the code, see what happens. So we can see the first value, 300, is 255 when it's cast to unsigned 8. Okay, because yeah, 255 is the max value and the 8-bit depth. Negative 100 as U8 is 0. Okay, interesting. And then nan as U8 is 0 as well. Interesting. It's just things to keep in mind. Next, let's move back to the docs. Had enough with casting. We're going to move on to literals. So, excuse me for a moment. Numeric literals can be type annotated by adding the type as a suffix. We kind of looked at that a little bit before. So, as an example, to specify the literal 42 should have the type I32, right? 42 I32. The type of unsuffixed numeric literals will depend on how they are used. If no constraint exists, the compiler will use I32 for integers and F64 for floating point numbers. Okay, back to the code. change back into the 05 types directory, create a new cargo project called literals. All right. Let's open up main.rs. Let's declare some variables or some values. So let x equals 2 u8, y equals 4 u32, and then let z equals 6 float 32. And now we're gonna, and so those were examples of suffixed literals. Now let's do some unsuffixed literals. So first we'll do let I equals 2, and then let f equals 1.0. And so here we can now compare the default behavior that Rust applies to unsuffixed literals as compared to that of suffixed literals. So let's just do a couple of print statements real fast. And to save myself some time, I'm going to copy paste a bunch of these. Yeah, 5 should be enough. Size of x in bytes. Okay, and then actually I preemptively copied. It happens. Okay. That's good. Now x, y, z, I, f. Should have written like a function to do this, but I'm a little lazy. Next time. But yeah, this is like functional. This is definitely deserving of some kind of automation. If you ever need to print out the size of your variables in your script, don't do it by hand. Okay. Looks good. Now let's run the script. Change into literals before I forget. Cargo run. Size of x is 1 byte. Size of y is 4 bytes. So the default size for unsigned 8 is 1. Or I guess just the size of unsigned 8 is 1. Size of unsigned 32 is 4. Size of float 32 is 4. Size of 2, the unsuffixed 2 is 4. So you can see it defaults to unsigned 32 or integer 32, which is what the compiler said or what the doc said. And then f is 8 bytes large. Interesting. So that's the biggest float 64. Okay. That was our whirlwind tour of literals, but there's actually a little more. There's some concept used in the previous code that haven't been explained yet, and there's a brief explanation for the impatient readers, namely the size of val function that we imported with the full path. People can use full paths or import it at the top of a file, but yeah, that's about it. Nothing too wild. Inference. So the type inference engine is pretty smart. It does more than looking at the type of the value expression during an initialization. It also looks at how the variable is used afterwards to infer its type. Here's an advanced example of type inference. Let's create another cargo project. Cargo new inference. cd inference. Open up main.rs. Remove the boilerplate. Replace it with, let's create an element or a variable called lm. Let's give it a value of 7u8. Next, let's create an empty vector that's mutable. So it's a growable array. After this, let's push the element or the variable lm onto the array, and onto the vector, and I already caught a typo in my code. Forgot an equal sign. Okay, and then finally, we'll use our old friend, the println macro, and our friend, the debug format, to print out vector or vec. Okay, we'll save that code. Cargo run. Ooh, we got an error. Oh yeah, that's why I was trying to vec push vec. I need to do vec push lm. Thanks. Thanks, compiler. A cyclic type of infinite size. Yeah. Yeah. Okay, so 7. That makes sense. And so the thing is, there was no type annotation needed anywhere after the initial declaration of lm. When we pushed the lm onto the vector, it didn't have to be declared with a type. It just knew. So that's pretty chill. If we don't print out, or if we don't do the push step, and it's just the empty untyped vector, let's see what happens. It's angry. So here it does not have an explicit type. So it's not inferring that there's a type from the lm variable. So we'd actually have to declare the type. But we don't have to worry about that now, thankfully. But if you wanted to, the compiler even gives you the syntax on how to do that. And I believe this should work. And if not, yeah, it works. Sweet. Just an empty vector. Cool. What happens if we push the element onto that type annotated vector? It's redundant, but yeah, we get the same value. Say type annotation is redundant in this case because of inference. Sweet. Awesome. We're on our final lesson for today of Rust by example and types. So let's return to the docs. Aliasing. So the type statement can be used to give a new name to an existing type. Types must have upper camel case names, or the compiler will raise a warning. Excuse me, I'm sounding hoarse. Need some water. The exception to this rule are the primitive types usize, f32, etc. Okay, so as usual, let's get back to the code. Change back to the main subdirectory for today. Cargo new. Let's do aliasing. Let's change into aliasing. And then let's get started with tweaking the main.rs. So actually before that, We'll leave the boilerplate there for a moment. Let's declare some types. So, nanosecond. Oh, I spelled type with a flip. It's okay. There's nothing wrong with the typo as long as you fix it. It's just part of life. Wisdom with Alex. Just imagine myself in many years. It's a grizzled old engineer sharing my wisdom on camera with the youth. What a sight to behold. Okay. So we have some types. They're all just aliases for unsigned integer 64. So let's get into the main function code. So let nanosecond of type nanosecond equals 7 as U64. Next, let's do inches of type inch equals 54 as U64. And finally, our old friend, the println macro, nanoseconds plus, where's the plus? There it is. Nothing wrong with typos as long as you fix it. That's the wisdom for today. We'll have to look up more for next time. I'm not that wise yet, so it's a limited fountain of wisdom. Okay. And then they just did a line split to make it a little nicer looking. So nanoseconds, inches, and nanoseconds plus inches. Save that. Cargo run. 7 nanoseconds plus 54 inches is 61 unit. While the computer lets us do this, it is not necessarily an intelligible result, but you can see that we get something returned. And so the main use of aliases is to reduce boilerplate. For example, the IO result T type is an alias for result T IO error type. Okay, so sometimes you might want to alias a type, but sometimes you don't. So it really just depends. It's a judgment call you have to make as an engineer and a problem solver. But yeah, if we return to the docs, in summary, today we covered types. You can see that was chapter 5 in the Rust by Examples documentation. We're well on our way. Okay. We are well on our way. But thank you for joining me on this adventure and learning Rust with me. I really appreciate your company and look forward to the next video. This has been Alex with Code Along with Alex, and see you next time.